Okay, we're back to talk about speed and velocity. So, we have so far talked about position, distance, and displacement, how we're going to use them in AP Physics 1 in this course. Now, obviously, the next thing we have to talk about is our speed and velocity. It's the next step up. So, they are different things, and you remember that from last year. Speed and velocity are not exactly the same thing. They can be the same in some circumstances, but speed and velocity for a certain object do not have to be the same thing. I would say that speed is a measurement of how much an object moves over time, whereas velocity is the rate of change in position over time. And those two definitions sound very, very similar, but you'll see once we get to the equations that they're really not. Before we get to the equations, we're going to talk about the difference between instantaneous speed or velocity and average speed or velocity. With instantaneous speed or velocity, what we're talking about is a measurement of these things at one instant in time. So measurement at one instant. Okay, and an example of something that measures the instantaneous speed or velocity would be a speedometer, okay, like on your car. So that is hooked up to how much the wheels are rotating, the rate at which they're going around, and it tells you exactly how fast you're moving right now. It does not tell you an average speed. It doesn't tell you, or it's not meant to tell you your speed over some large interval of time. And that's what an average speed is. Measured over an interval. Okay. So I'm going to give you the two equations for these equations are for average speed and velocity, I should note. So the following formulas are for calculating average speed or velocity but I'm going to put a caveat on there. For the limit as t goes to 0, they approach instantaneous speed or velocity. Okay. So here's what I mean by that. Let me give you the two formulas. The formula for average speed is V with a little line over it. Now, please remember, that means average, okay? That is not the same thing as this. If you see delta V, that is totally not the same thing as this. That means change in speed. This is average speed. They're two different things. Average speed is equal to d over t, where d, remember, is distance, and t is simply time. Okay, and this is a scalar. So this shows you how much an object moves over time, because d is how far the object has moved, okay? It's, again, the example I gave is if you had an object, you coated it in paint or something, and then it moved or rolled over a surface, and you measured the paint trail, you would get the distance that that object moved, okay? That would be distance. So the average speed is distance over time, how much an object moves over time. Average velocity is a little bit different. Okay, So average velocity, we still use the same symbol actually, so that's a little confusing. It's still v with the hat, with the line over it. And that's going to be the rate of change in position. Well, position is x, change is delta, so we have delta x over t. And that can be expanded to x minus x naught, because we can always expand any delta something into the final minus the initial. So in this case, x minus x naught over t. Okay? And we know that this is a vector. Okay, so the direction matters. Just like with displacement, and that's really what this is, displacement over time. Displacement is a vector. If you want to know where an object ends up, you do need to know how far it moved and in what direction. So it makes sense that since this is displacement over time, this would also be a vector. Your velocity needs to have a direction. Was your speed to the north, to the south, to the east, to the west? What direction was it in? And I'm just gonna write magnitude and direction are necessary. And I'll give one example. Okay, earlier we did the example between the difference between distance and displacement. Distance on a track, if you do one lap, is 400 meters. Your displacement, if you start in the same spot that you ended up in, is 0 meters. So let's say you do one lap on the track in 80 seconds. Your average speed is going to be v with a line over it, v hat equals d over t. Your distance was 400 meters, your time was 80 seconds, so that's 5 meters per second. Almost did the wrong units there. That would be your average speed. Your average velocity, on the other hand, would be v equals delta x over t, and I'm just going to move down here. V hat equals x minus x naught over t. If you started and ended in the same spot, you could say these are both 0. So it's 0 meters. Your position has changed 0 meters in these 80 seconds. It doesn't matter that your position wasn't always at that spot. It just matters that at the start and end, your position is 0 meters. Therefore, your average velocity is 0 meters per second. And that's totally fine. You can have a speed, you can have a non-zero speed and still have a velocity of 0 meters per second. Nothing wrong with that. So really what this really boils down to is you really need, if you're given a speed or a velocity and you're a little confused, you're like, oh, how could that be 0? You really have to know the context of the situation. Okay, so that's a little bit about speed and velocity. We're going to move on to acceleration now, and we're mainly going to focus from here on about velocity. Velocity was the rate of change in position over time. How quickly was your position changing? Okay, well, acceleration, as you probably remember from last year, is the rate of change of velocity over time. So you could say that acceleration is the rate of change of the rate of change of position over time, which is a little confusing. Basically, we know the position is changing, but the rate that the position is changing at, is that itself changing? Okay, is the rate that it's changing increasing? Is the rate that the position is changing decreasing? There's a formula for this. The definition for acceleration, symbol A, is, since it's rate of change of velocity, velocity is v. Since it's rate of change, that means we're going to have a delta v over t. And we could expand that to be v minus v naught, where v is final velocity, v naught is initial velocity over time. And this is always a vector. Let me move this up to make sure you guys can see it all right. Okay, we're good. All right. Last year we talked, there are 3 different ways that an object can accelerate. There's 3 different ways that an object can have an acceleration. Obviously, you could, let's say your initial velocity was smaller than your final velocity, so you could increase your speed. You could speed up. That's what we call speeding up. You could slow down. Or another way to change your velocity, since it's a vector, it has both magnitude and direction. Speeding up and slowing down change the magnitude. What if we just change the direction? That is also acceleration. Okay, and let me pause for a second here and just point out that, yes, I know that you guys talked about forces last year. I know you talked about circular motion. I know you talked about all this stuff. The way I usually run this class is I'm not going to mention a lot of those things until we get to them, okay? I'm going to treat it like we don't know anything about those other units, because everything that we do, with maybe one or two exceptions, can be solved with what I have already taught you in this class. We're going to leave those things like forces, circular motion, energy, momentum, waves, all that stuff, we're going to leave it until we get there. Right now, our sole focus is on kinematics. Anyways, back to this. The 3 ways to accelerate. Are to speed up, slow down, or change direction. Okay, so an object can either speed up, slow down, or change direction. Changing direction still counts as acceleration. And just a note about what we're going to study in terms of acceleration this year. We only deal with constant acceleration. And I'm going to put in parentheses for math problems. Okay? As far as math goes, if you're being asked to solve some sort of equation, or an equation is necessary to solve what you're doing, it's going to be a situation with constant acceleration over some period of time. Now, there could be multiple different periods of time that you're looking at, and they all have their different individual accelerations, but the acceleration won't be changing within those periods of time, if that makes any sense. Your acceleration can change instantaneously from one thing to the next, from one point to the next point, I should say, but it's not going to increase or decrease at a steady rate, okay? So, A might vary between periods of time, but change will not be continuous. And that's good, because things get really messy when you have continuous changing acceleration. The equations get a lot more complicated. Okay, so there's speed and velocity and acceleration. We have the definitions, we see some equations. Let's see some more equations. Let's see the kinematics equation, because so far, the equations that you have, they are simply definitions. Definition of average speed, definition of average velocity, definition of acceleration. But you remember from last year that there are kinematics equations here, here, and here that we use to solve a variety of problems. And these equations come out of the definitions that we just had. I could spend the day deriving those for you, or I could spend a whole video deriving those for you along with a couple other equations, but you're not really interested in that, and you can do that on your own if you're interested. I'm simply going to remind you of what those equations are. So I'm going to box them in. I'm going to start with this one, which we just saw. This is not the so that's not the equation I want to get to, but we can rearrange this, okay? How could I rearrange this? What if I multiply both sides by t? What I would end up with is at equals v minus v naught, and then if I add v naught to the other side, and then I do a little bit more rearranging, I just switch the sides, I end up with this, v equals v naught plus at. And that is the first kinematics equation that I want to talk about. It's simply a rearrangement of this. They are the exact same equation. This equation, you might say, looks familiar, because if I just put an f here and an I here, this would be the Fiat equation that we talk about in Regents physics. This is the same exact thing. We just have different labeling for the v and the v naught. It's the exact same thing. I'm going to show you how the other kinematics equations are similar. Last year, we had this one. Sometimes people call this the distance equation. D equals VIT plus 1/2 AT squared. Well, let's try and translate this, okay? 1/2 AT squared, all those variables are the same. Instead of vi, we're going to have v naught this time. T can stay the same. And d, this is a little problematic because d here really stands for displacement. It's not necessarily just distance. It's a displacement. And for displacement this year, we're talking about x and then x minus x naught. So imagine I had x minus x naught here, and then I just added the x naught to the other side. The second kinematics equation looks like this. X equals x naught plus v naught t plus 1/2 a t squared. Notice, this is exactly the same. I just changed this from a vi to a v naught. They're the exact same thing, except this is just the variable that we use now. And x equals x naught, again, imagine that I brought this x naught back to the other side. It would be x minus x naught, and that is just the symbol for displacement, and then it would look exactly the same. So here's your second kinematics equation. Again, the reason this one is better than d equals vit plus 1/2 at squared comes in the fact that now we're allowing for that initial position to not be 0. If I said that the object starts at, let's say, x equals 4 meters, before we would have had to remember that. We would have had to remember that and then add on 4 meters at the end. Now it's built right into the equation. There's nothing for us to remember. Let's change that third kinematics equation in a likewise fashion. It's this one right here, vf squared equals vi squared plus 2ad. You can probably guess how we're going to change that. This time it's going to be v squared equals v naught squared plus 2a x minus x naught. It's really important that you get comfortable with these and that you feel okay with using these variables. I know you guys are just getting to the age where you're comfortable working with variables and you're comfortable with solving things like this. Trust me, it's not scary. All we're doing is calling stuff by a little bit different name. And why am I doing that? Because the reference tables for AP Physics are very slightly different. Okay? I am going to throw one more equation in there at you, and this is a new one. And that equation is as follows. Average speed, or average velocity I should say, and notice that we already know that this is equal to delta, or delta x over t, but there's another thing that this is equal to, v plus v naught over 2. You might say, why didn't we learn this last year? Well, it wasn't really important last year, and they didn't ask questions about it. Average velocity, think about how you normally would take an average. Think about if you're driving a car. Okay, car advertisements say all the time, oh, our car can go from 0 miles per hour to 60 miles per hour in such and such a time. Over that time period, if I were to ask you, well, what's the average speed over that time period from when you're going from 0 to 60? A reasonable guess would be 30. Okay, why is that? Because it's the average of 0 and 60. It works if you didn't start at 0 either. If I said, okay, your car starts at 20 miles per hour at a certain time period, and then you speed up until it's moving 50 miles per hour. What's the average speed? And if you're dealing with constant acceleration, like we do in this class, oh, that's the thing, the car is speeding up at a constant rate, the acceleration is constant, you might say, well, the average speed would be 35 if you started at 20 and ended at 50. And the way you would get 35 is you would say, okay, well, how do I find the average of those two numbers? I add them together and divide by 2. All this equation is saying is that if you want to know an average velocity, simply take the initial speed, or initial velocity, add it to the final velocity, divide by 2. Very simple way to take an average. This equation doesn't get used a lot, but it is useful in certain cases, okay? It is useful if A is unknown, but assumed to be constant, and V and V naught are both known. We know what they are. Okay? That's where this would be really, really useful. Okay? So there's 4 kinematics equations. With these, you should be able to solve any kinematics equation that you come across, and any combination of these. Sometimes you have to use 2 different equations. Now, the other thing I want to point out, okay, so a couple of things actually. Notice that all 3 of these contain the acceleration term. They have a changing mix of speeds and positions and times, but all 3 of these contain acceleration. The reason I say this one is important if you don't know the acceleration is because you don't need it for this example. Okay? Now, the other thing I want to talk about is these equations are great for constant acceleration situations. But again, if you have a situation where the acceleration is changing over time, or you have multiple different parts of an object's motion. We'll do that this year. We'll look at different, some sort of complex motion that we can break down into a sequence of constant acceleration little episodes or chunks. Every time the acceleration changes, you need new equations. Okay, you need a new equation. So, for instance, there's one example with a rocket blasting off and then it coasts upward, and then a parachute deploys. In all three of those situations, there are different accelerations for that object. To model the speed, you would need at least 3 different equations. It could be 3 of all the same equation. But every time the acceleration changes, that is the key, that is the clue that you're going to need another kinematics equation, at least one more kinematics equation. I'm going to stop there. We'll do one more video with the examples and proportionalities, which is kind of a neat little shortcut that you can start using. Then we'll be done with the basics and we'll move on to graphing.